In this online lecture, we are going to study about nucleophilic aromatic substitution. So before going to nucleophilic aromatic substitution, let us recall electrophilic aromatic substitution. What we did in that one was this, that if we have a benzene ring and then an electrophile, then what will happen is then this benzene ring will go ahead and attack this electrophile, so that we have these three resonance structures which we are going to draw. So what will happen first is this thing. So this will go ahead and attack here, and then you have a substitution here on the benzene ring. So these are the bonds which are undisturbed. Let me redraw it for you. So we have this thing, and then let's say your electrophile gets attached here, and you have a plus charge, positive charge here due to loss, and then you know resonance can happen here. Okay, so what will happen? This can move here, this bond can move here. I will show you. This can move here. So what will be the result of that? So this is your undisturbed, and this one moved here. So you have a bond here, and then you have the plus charge here. You have electrophile here. This is your second resonance structure. What is the third one? This is your benzene ring. Okay, and then what can happen? This one can move here. Okay, now it's a turn of this bond to move here. Okay, and then let's draw the outcome of this move. So this will move here like this. Okay, and then you have the plus charge here, and then you have electrified here. Okay, so what would be the thing? And then some base will go ahead and attack, grab this one. There will be a base. Okay, so this aromaticity will be resumed, as you can recall from the previous online lecture. And then you have this electrified. So if you can recall, there is a proton here. So this base will grab this proton, okay, and this aromaticity will be resumed, right? This is what we did last time as well in our electrophilic aromatic substitution online lecture. And now today's topic is this NAS, which is nucleophilic aromatic substitution. So what happens here is this thing, you have a benzene ring. So this is your NAS. So let's quickly draw the benzene ring, and then now let's say we have a halogen over here on the benzene ring, and we can do completely different set of reactions. If we have a nucleophile attacking on this benzene ring, so instead of this benzene ring attacking, okay, like here on the electrophile, so this nucleophile will go ahead and attack on this benzene ring. So let's see what will be the result of that. So what do we have next is the attack of the nucleophile. Let's say it will attack here. Why it will attack here? Because this is a carbon and halogen bond, and as you know, halogens have greater electronegativity as compared to carbon. So this electron pair will lie more closer to the halogen as compared to this carbon. So this carbon will be the most positive site over here in this benzene ring. So this positive carbon will invite the attack of this nucleophile. Okay, so what would be the result of this attack? Let's go ahead and draw that. So you have this benzene ring here, and then these are your bonds here, and this one got attacked here. So you have your halogen here, and then you have your nucleophile here, right? And since this bond will be pushed here, carbon has a capacity of forming 4 bonds, right? So this bond will be pushed here, this electron pair of this bond will be pushed here, forming the negative sign over this one, and then again you can do the resonance here. Resonance is possible here. So let's see how. So this bond can move here. I'll show you. And so this can move here, pushing this bond over here, right? So let's go ahead and draw quickly that. So you have this benzene ring, okay? Then you have these two over here. And since this one is pushed here, so you have a bond here. And then you have the negative charge here. So this negative charge can move here in the benzene ring, okay? Like this positive charge. And then you have this bond here. And what would be the next resonance structure that is possible? So the next possible structure is this one will move here, pushing this one here, right? So let's go ahead and draw that as well. So this is your benzene ring, and then this is your bond here, and since this one got pushed here, and you have the negative charge here, and you have X and nucleophile here. So these are your three resonance structures that are possible over here. These are the intermediates right here, like we have in this electrophilic aromatic substitution. So these intermediates, this is energetically less favorable situation over here. So this is going to be the rate determinants step. This would be the slowest step, right? And then what we have is this one. What would be the next thing? So this negative charge over here, so there is, I'm going to draw this one as this is confusing a little bit. Let me draw it. So what we have over here is this benzene ring, and there is a bond here. This one moved here, okay, and this one the negative charge over here, and then you have X over here and nucleophile. So what would be the next step? So the next step would be this. So this one will be pushing over here and kicking this leaving group or the halogen out, okay? So this halogen will be the leaving group here. It will leave, and what we have left is we have restored the aromaticity of the benzene ring, okay? So we have these aromaticity intact here, and we have successfully put the nucleophile on the benzene ring, which was not possible as such on the benzene ring alone. But this X or the leaving group or the halogen is helping us to put this nucleophile on the benzene ring. Okay, so we are used to doing electrophilic aromatic substitutions. We are used to putting electrophiles on the benzene, be it Friedel-Crafts, alkylation, acylation, and so many other examples. Nitration of benzene, sulfonation, right? But here what we are doing, we are trying to put nucleophile on the benzene ring, okay? Now we'll see some other examples here. Now what we want to learn here is this thing, that putting a nucleophile on the benzene ring, we go through these intermediates which are energetically less favorable, right? So these are we want to create a situation where benzene ring would be made more favorable to the attack of these nucleophiles, because benzene ring, due to its aromaticity, is extraordinarily stable. And if we want to disturb the stability of this molecule, so we do know that these electrophilic aromatic substitutions and nucleophilic aromatic substitutions, they have one thing in common, that is this intermediate generation. This is the slowest step, and it is also energetically less favorable, because we are destroying something which is very stable. So to create such a situation, to force such thing, we do need to create a situation where these things are where these nucleophile will go ahead and attack and create this situation. So what do we want to do is, we want to put electron withdrawing groups on the benzene ring so that we can create such situation. Let's look into that. So here we have, let's say, your nucleophile, okay, and then let's say we put nitro group here. So nitro group, if we see, is something like this. So what it would do is, it would try to withdraw the electron towards itself. Okay, and we do have this negative charge over here. So this is one of the intermediate which I've drawn for this. Let's say it's the situation over here. Okay, and we have this negative charge. Okay, so what if we have an electron withdrawing group over here? So let's see how this is gonna make the the attack of nucleophile more prone to this benzene ring. This how this electron withdrawing group would help this situation. So we know that this can move here, and this pi bond would be pushed here. Okay, and what can happen here is this thing. So when this pi bond is moved here, okay, to this, it can move here to the nitro group. Okay, so it can and this electron density can move all the way up here. So let me draw it again. So what I'm trying to say is this thing. So you do have this thing over here, right? So this one moved here, and then this pi bond can be made to move all the way up to the nitro group. Okay, and this would move here. So there is a double bond here. So this is our situation right here. Okay, so this positive charge on the end makes it electron withdrawing, right? So this pi bond can move all the way up here to the nitrogen, and then this bond can be kicked further towards the oxygen, moving this all the way up to the oxygen. Okay, so this is how it would look like in the resonance structure. So you have your benzene ring, your X and Nu, and then you have your bond here. And then since this one moved here, so I have a bond here, and this N looks like this. So you do have oxygen here, and then you do have this oxygen since this one moved here with the negative bond. Okay, and this one is already here. So this is your resonance structure. So electron withdrawing groups, they stabilize the situation here, because you do know the fact that when the charge is able to move to the greater portion of the molecule, that leads to the stabilizing effects, and it does lead to a stabilized intermediate, right? And this is something we are looking forward for. And so electron withdrawing groups on the benzene ring, they stabilize the intermediate, and more make them more favorable to the nucleophilic attacks. Just in the same way, electron donating group on the benzene ring does invite the attack of electrophilic um molecules, right? So electrophiles, and making it more prone to electrophilic aromatic substitutions. Because if you see here, we do have a positive intermediate here. And if we have something which donates electron and stabilizes positive charge on this intermediate, would stabilize the conditions here. And similarly, we do have a negative charge over here. And if we have some electron withdrawing group, then that would favor the situation, because it would withdraw that negative charge and separate it more over the molecule, and it would favor that situation. So anything that withdraws this negative charge, that would stabilize that intermediate. Okay, now let's see. Now let's go ahead and look into some examples now that we do know about the basis of the nucleophilic aromatic substitution. So let's look at some leaving group trends here. When we talk about leaving groups, we do talk about halogens. So who's the better leaving group here? Fluorine, chlorine, then we have bromine, and then iodine. So what do we want to learn here is that when we have this benzene ring, let me draw it again. So when we have this benzene ring, and let's say we have this fluorine group over here, then what do we want to learn here is this thing. So fluorine is the best leaving group here, because we do want to attack here with the nucleophile, and when this step happens, this is a very slow step, as you know, because it is going into something which is energetically less favorable, and anything that makes it more favorable will be energetically favored. And because carbon fluorine bond is the most polarized bond as compared to carbon chlorine, carbon bromine, and carbon iodine bond. Because the polarity of the bond is the most here, making this the most partially positive carbon in this situation as compared to the others, because the electronegativity of fluorine is the most, so making it the most positive carbon here. So what would be the leaving group? So fluorine would act as the best leaving group as compared to chlorine, as compared to bromine, and as compared to iodine. So let's look into one example here. Let's say we have this benzene ring, and then we do want to put some nucleophile here. Let's say it's any nucleophile. So let's say we have this example over here. We have a fluorine, which is a leaving group here, and this benzene ring have a nitro group, which is the electron withdrawing group, and we want to put OH group here, which is the electrophile, not the nucleophile. So what would be the result of that? We do need to do what would be the result of this reaction. So we will see that we have I'm sorry, just, let's yeah. So let me draw it in the similar way. You can draw it like this also, but let's follow the benzene, the bonds I've drawn here. So what would we will see that we do put OH group here, the leaving group would leave, and we are able to successfully put this OH group, which is a nucleophile here, on this benzene ring. So this is one of the example of the nucleophilic aromatic substitution. Now let's look into the mechanism of this reaction. So we have this benzene ring over here, and then we do have this chlorine, which is the leaving group, which is going to be released at the end. And then to facilitate or to activate the ring towards the nucleophilic attack, we attach it to the nitro group. And whenever nitrogen has five bonds, so sorry, four bonds here, one, two, three, and four. So it possesses a formal positive charge. And then what will happen? This nucleophile is going to attack on this carbon, which is attached to the leaving group, because this is the polarized bond here, and this carbon, which is over here, possess partially positive charge, right? So it will go ahead and attack here. And what would be the result of that? I will show you by drawing. Just one second. So there's a CL group here, and this OH gets attached here. What will it do? It will push this attachment of OH, will push this pi bond over here. Okay, and then there would be a negative charge here. And then what it would do, that negative charge causing these bonds to move here, and this will push the bond here. Okay, so let's go ahead and draw this. This one would move here, and how it would look like. So there's a bond here, and this one moved here. Okay, and compensating this positive charge, and this one would move here. So let's go ahead and draw the rest of the things. So you have the bond here, and what else is left? So you have this O, and whenever it has 6, it does have a negative charge, and then this one is pushed here, making oxygen negatively charged. So this bond pushed here, making 2 electron pairs. We're here putting a negative charge. So this is your situation. So what we forgot here that this since this bond moved here, so there is a double bond here. Okay, and then this double bond, since nitrogen can form 4 bonds, so this pushed this bond over the oxygen. So now let's see what would happen next after this. So in the next step, the leaving group chlorine is going to leave this structure over here. So let's see what will happen. So this oxygen, let's try it with the yellow pen. So this will move here, this lone pair, moving this bond over here, okay, which will push this one bond back right here, and this will kick this chlorine out. Okay, so the same thing on the reverse of the steps are happening here. So this one moved here, this one moved back here. Okay, and this caused this bond to move over here and kicking this leaving group out. So let's go ahead and draw that. So this is the result of these movements here. So this one moved back here. This is a double bond. Okay, this bond moved here. So you have a bond here. So this bond get pushed here. Okay, and this chlorine left from here. So you just placed your nucleophile on the benzene ring with the help of this nitro group. Now let's learn why it is good to place electron withdrawing group over ortho and para positions.